G'day, mates. Have you ever looked up at the night sky and felt a sense of stillness? It's a common feeling staring into that vast, dark expanse, sprinkled with tiny, unmoving points of light. We see the stars, the planets, and distant galaxies, and they all seem locked in a timeless cosmic dance. For centuries, humanity believed our place in the universe was relatively fixed, part of a grand, predictable clockwork. But what if I told you that this perception of stillness is a magnificent illusion? What if, beneath this calm veneer, our entire corner of the cosmos is being pulled relentlessly towards something we cannot see? Something that lies beyond the very edge of our known universe. This isn't just a wild idea from a science fiction novel. It's a genuine cosmic mystery that has puzzled astronomers for years. Imagine you're on a raft in the middle of a vast ocean. You can see the water for miles around, but you notice your raft is moving in a specific direction, even though there's no wind and no visible current. To truly appreciate why this dark flow is so astonishing, we need to understand how we expect things to move in the universe. According to our best models, everything should be moving away from everything else. Think of it like baking a raisin loaf. As the dough rises, every raisin moves away from every other raisin. So, how on earth do we measure something as subtle as the movement of giant galaxy clusters billions of light years away? The key is an incredible relic from the dawn of time, the cosmic microwave background, or the CMB. This isn't just any light. It's actually the oldest light in the universe. For the first 380,000 years after the Big Bang, the universe was a super hot, dense soup of particles and radiation. But as the universe expanded and cooled, atoms formed, and suddenly light was free to journey across the cosmos unimpeded. This first burst of liberated light is what we now detect as the CMB. It's a faint microwave glow that fills the entire sky, coming from every direction. You can think of it as the universe's baby picture, a snapshot of what the cosmos looked like when it was just an infant. Armed with this incredible cosmic backdrop, astronomers devised a clever technique to clock the speed of distant galaxy clusters. The method relies on a subtle interaction between the clusters and the CMB light, an effect known as the kinematic Sunyaev-Zeldovich, or KSZ effect. The same thing happens with galaxy clusters and the CMB. As this entire cluster moves through the sea of CMB photons, the hot gas scatters the ancient light. The story of the dark flow's discovery isn't about a single eureka moment with a telescope. It's a tale of persistence, meticulous data analysis, and a team of scientists brave enough to question a fundamental assumption of cosmology. This is exactly what Alexander Kashlinsky and his team at NASA's Goddard Space Flight Center did. They spent years meticulously analyzing data from the WMAP satellite, stacking the signals from nearly 800 different galaxy clusters. The first results from Kashlinsky's team were published in 2008, and they sent immediate shockwaves through the world of cosmology. After analyzing a catalog of 791 galaxy clusters, they unveiled their startling conclusion. Instead, they were all streaming in a single uniform direction toward a patch of sky between the constellations of Centaurus and Vela. The speed was also mind-boggling, somewhere between 600 and 1,000 kilometers per second relative to the cosmic microwave background. The most baffling aspect of the dark flow discovery was not the motion itself, but the complete absence of a cause. When astronomers looked in the direction it was coming from, they found nothing. At least nothing out of the ordinary. The culprit responsible for hijacking a huge chunk of the cosmos was, for all intents and purposes, completely invisible. This is why the name dark flow is so fitting. So what makes this dark flow so utterly strange? Well, it's because this discovery doesn't just challenge a minor detail in our cosmic models. It strikes at the very heart of one of our most fundamental assumptions about the universe. The dark flow spits in the eye of this principle. It suggests there is a special direction. It creates a cosmic axis, a preferred line of travel towards the constellations of Centaurus and Vela. This anomaly forces us into a very uncomfortable position. Either the measurements made by Kashlinsky and his team are wrong, perhaps due to some subtle, unaccounted-for error in their incredibly complex analysis, or our most successful and elegant model of the universe is wrong. This is a classic scientific dilemma. Do you trust the model that has explained so much, or do you trust the challenging new data? One of the most compelling, though mind-bending theories to explain the dark flow is that it's caused by a massive structure that lies beyond the edge of our observable universe. Imagine the universe before the Big Bang, in a period physicists call inflation. This relic structure would be a gargantuan concentration of mass left over from the universe's first moments. It would be an ancient cosmic fossil, a ghost from the inflationary era. Some of the most mind-bending theories propose that the dark flow could be the gravitational signature of another universe entirely. In this cosmic vision, our entire universe is just one three-dimensional brain floating in a higher dimensional space known as the bulk. But gravity is different. Gravity, in this picture, is not confined to our brain. It's the one force that can leak or propagate through the higher dimensional bulk from one universe to another. So where do we go from here? The quest to solve the mystery of the dark flow is far from over. In many ways, it is just beginning. Upcoming missions like the European Space Agency's Euclid satellite and the ground-based Vera C. Rubin Observatory in Chile are specifically designed to tackle these kinds of large-scale mysteries. They will conduct unprecedented surveys of the sky, mapping the positions and measuring the motions of billions of galaxies with a precision that was once unimaginable. The journey to understand the dark flow is a perfect illustration of the scientific spirit. It is a story of curiosity, perseverance, and the courage to question our most fundamental assumptions. It reminds us that the universe is under no obligation to make sense according to our current theories. The anomalies, the things that don't quite fit, are often the most exciting parts of science. As we draw our cosmic journey to a close, we find ourselves standing before a profound and persistent mystery. The biggest questions, of course, remain tantalizingly unanswered. First and foremost, is the dark flow real? The dark flow, in its ambiguity, has become a powerful mirror, reflecting the limits of our knowledge and the vastness of our ignorance. The story is not over. The next chapter is about to be written. Whether it turns out to be a gateway to a new understanding of gravity and the multiverse, or a cautionary tale about the subtleties of cosmic data, its legacy is secure. Ultimately, the dark flow mystery is an invitation to keep looking up, to keep asking questions, and to embrace the unknown. It is a humbling reminder that even after centuries of astronomy, the universe still holds deep secrets, and there are vast dark currents moving just beneath the surface, waiting for us to find them.